In this video, we are going to derive the constitutive relation between stress and strain used for plane stress and plane strain problem, because we are going to analyze the plane stress and plane strain problem in finite element. So we have to know the basic relation between the stress and strain in three-dimensional. So consider a three-dimensional element which is subjected to the normal stresses and shear stresses, shear strains, etc. So the three planes consisting of different stresses. If you consider the strain in x direction, the strain value is sigma x by E, and the other direction strains are minus sigma by E into the Poisson ratio. So we are, if you have some stress in x direction, there will be the reduction in the size in other two directions. So the strain will be in negative in other two directions if you consider any one of the direction. So with this concept, we are going to derive the relation between, stress to strain. So it is stress-strain relationship with the strain displacement constant. So here all the equations are converted to stress component. For this, initially we have to write the strain in x direction, that is epsilon xx. We can write it is the strain in x direction by considering the force in x direction. It is represented by epsilon xx. So sigma x by E. At the same time, the strain in y direction by considering the loading in x direction, it is sigma y by E into nu. It is also in the opposite direction. Next one, sigma x z, it is minus sigma z by E nu. So the total strain in x direction, is written as epsilon x sigma x by E minus nu sigma y by E minus nu sigma z by E. So keep this is equation number 1. The second equation, similarly you can write epsilon y is equal to minus nu sigma x by E plus sigma y by E minus nu sigma z by E. So this is equation number 2. Epsilon z is minus nu sigma x by E minus nu sigma y by E plus sigma z by E is the third equation. So now our idea is to eliminate sigma y, sigma z by analyzing these three equations and coming up with the equation of only consisting sigma x. So now I am taking 1 and 2. Here if you compare sigma y term, it is one extra Poisson ratio is there. So I am going to multiply the Poisson ratio with the equation 2. So 2 into nu plus 1. So this is our concept. If you multiply the nu with this second equation, here minus is there, here plus, so automatically it cancel. So the second equation is multiplied with the nu. So nu into sigma y, which is equal to minus nu square sigma x by E plus nu into sigma y by E minus nu square sigma z by E. So the first equation, epsilon x is equal to sigma x by E minus nu sigma y by E minus nu sigma z by E. So you can deduct the values and finally come up with epsilon x plus nu epsilon y, which is equal to, if you take sigma x by E outside, so it is 1 minus nu square, minus if you take minus sigma z by E outside, so it is nu plus nu square. So keep this is equation number 4. So now next I am going to consider 1 and 3, and again I am going to eliminate sigma y. Here there is no multiplication of nu because the two equation having nu term. So only I am going to deduct 1 minus 3. So I am going to deduct 1 minus 3. So I am writing epsilon x is equal to sigma x by e minus nu sigma y by e minus nu sigma z by e, and epsilon z is equal to minus nu sigma x by e minus nu sigma y by e plus sigma z by e. So I am going to deduct. So minus plus plus minus minus plus plus minus. So we can cancel this term. So epsilon x minus epsilon z is equal to sigma x by e. You are taking sigma x by e outside. So it is 1 plus nu minus, if you are taking minus sigma z by e outside. So it is 1 plus nu again. So keep this is equation number 5. So now consider the equation number 4 and 5. Consider the equation number 4 and 5 and try to eliminate the stress sigma z, because we need the equation in terms of sigma x only. So consider the equation number 4. So I am going to write here again equation number 4. Epsilon x plus nu epsilon y, which is equal to sigma x by e 1 minus nu square minus sigma z by e nu plus nu square. So this is equation number 4. So compare this. If you multiply the equation 5 with nu, you will get this term. So I am going to multiply the equation 5 with the value of nu. So nu into epsilon x minus epsilon z, which is equal to sigma x by e. If you multiply nu plus nu square minus sigma z by e nu plus nu square, and going to deduct the value minus minus, and you can cancel this equation. Finally you got epsilon x plus nu epsilon y. You multiply the nu inside and put negative sign, nu epsilon x plus nu epsilon z, which is equal to sigma x by e. I am taking outside 1 minus nu square. If you multiply the negative inside this values, minus nu square, minus nu minus nu square. So we have to simplify this equation. If you take epsilon x outside, it is 1 minus nu, because this term and this term is having epsilon x, so it is 1 minus nu plus nu epsilon y plus nu epsilon z. Here you can write 1 minus nu minus 2 nu square. So here we can expand. So 1 minus 2 nu square minus nu. So we can write it is 1 plus nu and 1 minus 2 nu. So if you multiply inside 1 minus 2 nu plus nu minus 2 nu square. So you will get the same equation. It is 1 minus nu minus 2 nu square. So both are same. So we can rewrite this equation with these terms. 1 plus nu, 1 minus 2 nu. 1 plus nu, 1 minus 2 nu. So from this equation, I am going to get the value of stress and x direction, sigma x. By keeping sigma x on left side and bringing all the component to the right side, we will get the complete equation. Sigma x is equal to So it is sigma x is equal to, you multiply epsilon on the top, E, and you bringing this term to the denominator, E by 1 plus nu, 1 minus 2 nu, multiply with this 3 terms. Sigma x equal to E divided by 1 plus nu, 1 minus 2 nu, into epsilon x 1 minus nu plus nu epsilon y plus nu epsilon z. Now we have the relation of stress in x direction with all strain component. So keeping this is equation number 6. Similarly, we can write other equation without a derivation. Sigma y is equal to E plus 1, E divided by 1 plus gamma 1 minus 2 nu. We can call it as nu as well as gamma. Epsilon x nu into epsilon x plus epsilon y into 1 minus nu plus nu into epsilon z. So you have to multiply 1 minus nu with the corresponding direction. Now we are considering y, so I am multiplying 1 minus nu with the y direction. As for the other component, I am multiplying with nu. For sigma z, similarly we can write E divided by 1 plus nu, 1 minus 2 nu, nu epsilon x plus nu epsilon y plus plus epsilon z 1 minus nu. So this is equation number 7, this is equation number 8. So we have derived 3 components of a state of stresses. Another 3 component we are going to derive, that is shear stress. This is normal stress value. Next one we are going to derive the shear stress value. So the relationship between shear stress and shear strain. Because we are going to derive the shear stress with the help of shear strain. As in the case of deriving the stress with the strain component, we are going to derive the shear stress with the use of shear strain. For this, we consider the shear stress is shear modulus into shear strain, where the shear modulus G is equal to E divided by 2 into 1 plus nu. Hence, the shear stress tau xy can be written as E divided by 2 1 plus nu into gamma xy. Now we are going to multiply and divide by some component. So multiply the above equation by the previous equation by multiply as well as divide the previous equation by 1 minus 2 nu. So that tau xy is equal to E divided by 2 1 plus nu multiply by 1 minus 2 nu and divide by 1 minus 2 nu into gamma xy. So this is equation number 9. So we can write for the remaining term. Slightly I am going to modify E divided by 1 plus nu 1 minus 2 nu divided by 1 minus 2 nu into gamma yz by 2. So I am bringing this 2 to the last. Tau zx E divided by 1 plus nu into 1 minus 2 nu divided by 1 minus 2 nu into gamma zx by 2. Gamma zx by 2. So this is equation number 11. So we have derived all the components. Now I am going to make in the form of matrix. So in the previous equation of the stresses, we have E divided by 1 plus nu into 1 minus 2 nu. That's why we are multiplying to get the common factor of E divided by 1 plus nu into 1 minus 2 nu. 1 plus nu into 1 minus 2 nu. If you separate this term, you will get the matrix constitutive relation by 1 minus 2 nu by 2. So when I am writing the complete form of equation, you will understand. So this is very large matrix form: sigma x, sigma y, sigma z, tau xy, tau yx, yz, and tau zx. So this is our required format: sigma x, sigma y, sigma z, tau xy, tau yz, and tau zx. So directly I am writing the components. E divided by 1 plus nu, 1 minus 2 nu is common. So it is 1 minus nu. If you see sigma x equation, it is 1 minus nu is the coefficient for epsilon x, nu is the coefficient for epsilon y, and nu is the coefficient for epsilon z. So nu and nu. For the stress value, there is no component, so it is 0, 0, 0. Further, we have to write. It is difficult to draw the straight line. Next big pen. So I try to draw. So it is sigma epsilon x, because the relation for epsilon x, epsilon y, epsilon z, gamma xy, gamma yz, and gamma zx. So if you multiply this row, E divided by 1 plus gamma into 1 minus 2 gamma, which is equal to epsilon x into 1 minus nu plus nu into epsilon y plus nu into epsilon z. That is the equation we have derived here. So all other items are 0. So similarly we have to fill nu 1 minus nu 1 minus nu. So this is for stress equation. All other terms are 0. For the shear strain equation, we have tau xy. The stress components are now 0. So this 3 by 3 matrix is fully 0. We have to fill only the strain value. So if you see the last equation, E divided by 1 plus nu into 1 minus 2 nu is common. And the outer matrix outer vector consists of gamma zx, gamma yz, and gamma xy. So the inner value inside the matrix is 1 minus 2 nu by 2. 1 minus 2 nu by 2. So only one value is available, 1 minus 2 nu by 2. All other strains are 0. Here 0, 1 minus 2 nu by 2, 0, 0, 0, 1 minus 2 nu by 2. So this is the equation of relation between the strain and stress. Stress in relation with the strain. So here we can conclude, if you have plain strain value, you can eliminate epsilon z and gamma yz and gamma zx. You can neglect the rows and columns so that you can get only epsilon x row, epsilon y row, and gamma xy row. The last two columns are also eliminated. So finally we get the form of 3 by 3 matrix. Plane strain condition. Plane strain condition. It is epsilon z 0, gamma yz 0, gamma zx 0. By eliminating the rows and columns, you get sigma x, sigma y, and gamma xy only. So this is in the vector form. which is equal to E divided by 1 plus nu 1 minus 2 nu into 1 minus nu 0, because is the direction there is no value. So nu 1 minus nu 0 0 0, the gamma xy relation is 1 minus 2 nu by 2. So this is the constitutive relation with the epsilon x, epsilon y and gamma xy. Similarly for the plane stress, condition, very small derivation is there. Sigma is at 0, tau x is at 0 and tau y is at 0. So these are the conditions. For this we consider epsilon x equation without sigma is there. So sigma x by E minus nu into sigma y by E. So these two terms only available. So I am giving the equation number 12. Epsilon y is equal to sigma y by E minus nu into sigma x by E. So keep this is equation number 3. So now I am going to eliminate the sigma y term as in the case of previous derivation. So multiply the 13th equation with the nu. I am going to add 12 plus nu 13, the equation number. So it is epsilon x is equal to sigma x by E minus nu sigma y by E. Nu into epsilon y which is equal to, here I am putting sigma y by E first, this positive quantity, and minus nu into sigma x by E. So I am going to delete epsilon x plus nu into epsilon y, which is equal to sigma x by E. If you are taking outside, so if you multiply nu with this equation, I think it is minus nu square. So it is 1 minus nu square. 1 minus nu square. So if you get the sigma x relation here, it is E divided by 1 minus nu square into epsilon x plus nu into epsilon y. Similarly, you get the other equations from this equation, E divided by 1 minus nu square, epsilon y plus nu into epsilon x. And tau xy equation, tau xy is the equation from E divided by 2 1 plus nu into gamma xy. So if you want to get the similar denominator here, you have to multiply and divide by 1 minus nu, because here 1 plus nu is there, we need 1 minus nu square as denominator. So E 1 minus nu divided by 2 into 1 plus nu into 1 minus nu into gamma xy. So you get E divided by 1 minus nu square into 1 minus nu by 2 into gamma xy. So we can write in the matrix form also, sigma x, sigma y, tau xy for the plane stress problem. So E divided by 1 minus nu square is the common, and so if you read the first equation, epsilon x, it is 1, the coefficient is 1, here it is gamma. So I am going to put it is 1 gamma, there is no coefficient for tau xy, so 0. So gamma 1 0 0 0, the last derived form it is 1 minus gamma by 2, 1 minus gamma by 2, I am going to fill here 1 minus gamma by 2, which is epsilon x, epsilon y, gamma xy. So this is the plane stress equation, the constitutive models with the constitutive constants D. So this equation we are going to use in our numerical problem and derivation of finite element for the plane stress and plane strain cases.